All right, let's go ahead and get into it. Today we're starting section 4.2. We're talking about antiderivatives. We introduced antiderivatives back in section 4.1. And in that section, we were going over some basic introductory rules of how to take antiderivatives for kind of the most basic types of functions. Really what all of those we're taking the basic differentiation rules and kind of doing them in reverse. So we had kind of a counterpart to the power rule, and for the how to take derivatives of exponential functions and logarithms and things like that. And we kind of did all of those in reverse to go over how to do antiderivatives. Now, those are all great techniques, and we're going to use them, throughout chapter 4 here. But the set of rules that we came up with in section 4.1 is not enough to give us a means for finding antiderivatives for like larger classes of functions. So if this were a full course in Calculus 2, actually, so Math 401 at Sac City, we would spend a lot of time talking about all sorts of different integration techniques, all of which are designed to take antiderivatives of different types of functions, different combinations of functions. But this is not a full course in Calculus 2, so we have to kind of focus on just the essentials here. So this is really the only other technique that we're going to talk about, but you could make an argument that it's really the most important one, even compared to all of those additional techniques that you would learn about in a Calculus 2 class. We call this substitution, or usually it's called U substitution, which will make more sense when we get into it. But basically, if you kind of follow the pattern of section 4.1, where we find antiderivatives by looking at our differentiation rules and trying to do them in reverse, it would make sense to start thinking about some of the differentiation rules we haven't talked about yet. So there's the product rule, there's the quotient rule, there's the chain rule. The first two of those we're not going to try and find a counterpart for in the case of integration, but for the chain rule specifically, we will, and that's what this section is about. So to motivate the technique we're going to talk about here, consider this integral right here that we want to try and evaluate. It's the integral of 2x times the square root of x squared plus 1 dx. At first glance, you might be looking at this and seeing a product of two functions, so 2x times that square root function there. And so you might think this is something that would require whatever the counterpart of the product rule is for derivatives. However, we actually don't need that, because if you looked a little bit closer, you might also notice that we have a composite function in here. Ignore the 2x for a second. We have the square root of x squared plus 1. That's a composite function. And we know that for composite functions, when we're taking derivatives, we need the chain rule. So here, I'm going to see if there's some kind of reverse or some kind of, let's go with the word reverse of the chain rule for dealing with antiderivatives of this form. Okay, so here's that composite function again, square root of x squared plus 1. And remember what it is that we're trying to do. I want to think of this entire integrand right here, 2x times the square root of x squared plus 1, as the derivative of some unknown function. And if I can figure out what that unknown function is, I will have found the antiderivative of this. So I'm going to phrase this in those terms. Let's imagine a function h of x such that the derivative, or h prime of x, is equal to the thing that we were given here. Okay? So that means h is an antiderivative of that integrand. However, because we noticed this composite function here, I'm going to guess that h of x is also some composite function. In particular, I'm going to guess that h of x has the form f of g of x. And if that's true, then h prime of x can be evaluated by using the chain rule on this. Specifically, h prime of x would look like h prime of g of x times g prime of x. That is the chain rule, the way that we presented it back in chapter 2. So if this if this and this are both what h prime of x are equal to, then I can set them equal to each other. I'm thinking of h prime of g of x times g prime of x as being the integrand that we started with, 2x times the square root of x squared plus 1. In this left-hand side here, only one part of this function here is a composite function, that f prime of g of x. So I am going to guess that the composite function that I'm seeing on this side, in fact, I'll go like this. I'm thinking that this composite function, f prime of g of x, is probably equal to this composite function, because those are the only two composite functions that I see in the entire equation. If that's the case, remember, composite functions we can think of as having an inside and an outside. The inside here is the g of x, and the inside here is x squared plus 1. So I'm going to assume that this g of x is equal to x squared plus 1, which we have here. Okay, the outside function is the square root function, and over here it's what f prime is equal to. So I'm going to assume that f prime is equal to the square root of x. That way, f prime of g of x would be exactly this. Okay, now notice there's one additional part of the chain rule here. It's that g prime of x. That would have to match with whatever I did not account for yet on the right-hand side. G prime of x would have to equal 2x, but it is, because if you look at how we define g of x, the derivative of that is 2x. So that matches. What that means is that this expression, the integrand that I started with, has this form to it. And so if I can just reverse the chain rule and get this back into the form of f of g of x, I will have found that antiderivative, okay? Well, if we know what f prime is, and the goal is to find f of g of x, I can use the antiderivative of this much simpler function to find f. We've done this before, but just as a reminder, if you want to find the antiderivative of a square root, it's easier to write it as x to the 1/2 power. And then the antiderivative, by putting the power rule in reverse, would look like this, 2/3 x to the 3/2 power. And so putting all of this together, we have that the integral of 2x times the square root of x squared plus 1 dx is equal to, again, h of x. Remember, I'm assuming that h of x is an antiderivative for this, plus c, we have to have that plus c there. Then we said h of x we think is going to have the form of a composite function. So we're going to write h of x in this form, f of g of x plus c. But now we know what both f and g of x are. So I take g of x, the x squared plus 1, plug it in for the x in my f of x, that's forming a composite function, and I get this as a solution. 2/3 times x squared plus 1 to the 3/2 power plus c. This is my antiderivative. And I'm not going to do it here, but it's a good idea for you off to the side in your notes to verify that we did this correctly. And the way you verify that you did an integral correctly, an indefinite integral, which is what this is you take the derivative of your answer and see if you get back to your integrand, which is what happens here. But again, you can verify that. So this process worked, and notice we made use of the chain rule, but we kind of worked it in reverse. The problem is that felt kind of complicated to think through it in those terms. It felt sort of messy. And so what we're going to do is simplify this process to make to make it a little bit easier to manage. So to start with that, we're going to simplify the notation that we're using. To get a little bit more general, that was a specific example, but what we really did there is we had an integral of a function, and we chose to think of that function as being in this form, f prime of g of x times g prime of x dx, because this is the result of applying the chain rule to taking the derivative of this composite function, f of g of x. So doing that in reverse, taking an antiderivative gets you back to f of g of x, and then of course there's a plus c there. So again, the whole idea was that we thought of our integrand as having this form. Once we did that, we looked for something in there that could be thought of as a composite function and used that to figure out what g of x was, what f prime of x was, and then matched the g prime here with what we should be seeing. What I'm going to do is the function on the inside, the g of x, we're going to assign it a new variable. And kind of the standard variable that you'll see used in pretty much any textbook on calculus is u. We're going to set that inside function, that g of x, equal to this variable u. And then we're going to define something called a differential. So in these integrals here, we've already talked a little bit about this differential dx. We haven't talked about where it comes from, and we don't really get into a full discussion on that in this course. That's more left for a full calculus course. But when we make this change of variables, so we're setting g of x equal to u, we're going to define this du here to be equal to g prime of x dx. In other words, du is equal to everything that you're seeing right here. So what that means is that if I make those two definitions, then the g of x that appears in parentheses here can be replaced with a u, and then all of this stuff outside of this set of parentheses, the g prime of x dx, gets changed into a du. And notice that the integrand looks significantly simpler now. F prime of u du. The derivative of this, as we know, would be f of u, because that's an antiderivative for f prime. And then again, you have that plus c there. So when we rewrite an integral and solve it using this technique where we replace that g of x with this variable u, that's called u substitution, or sometimes it's just called substitution. But in this class, I'm going to be calling it u substitution most of the time. Okay, so to recap on this method before we start looking at examples, what we do is we find, to find an antiderivative of a function using this technique, it's this 5-step process. We look carefully at our integrand, and then we pick a function that we want to assign to the variable u. Now, typically, that function is going to be something that you can think of as the inside of a composite function. Although I'll say right now, it's not always obvious what that is. This requires a little bit more, it's a little less direct, I guess I'll say, than taking derivatives. U substitution sometimes takes a little bit of experience and takes a little bit of trial and error before you figure out what actually works. But the idea is to assign part of your integrand to be equal to that u, and then rewrite the integrand in terms of just that u, also with a du in place of a dx. Okay, that's actually step 2 here. So for step 2, whatever you set u equal to, you take its derivative to get g prime of x dx equals du, and then you make that replacement in your integrand, which is step 3. Step 3 is rewriting your integral entirely in terms of u and du. So what that means is that the integral should have no x's left in it once you've made this substitution. If you did this correctly, and if this is the type of integral where this technique works on in the first place, then what you should end up with is the integral of a simpler looking function, all in terms of u, which you should be able to integrate using one of the techniques from 4.1. Once you have done that, you're going to get an antiderivative, but it's all going to be in terms of u now. So then what you do is you substitute g of x back in for all of the u's to turn everything back into x's again. So that's going to make more sense as we work through examples, and we have several to work through just to get you kind of used to this. So let's start here. I want to use u substitution to try and evaluate these 3 integrals right here, starting with this first one. Okay, so if you look at the integrand, it looks fairly complicated, but the trick here is to pick a function that looks like it's inside of some composite function and use that to assign to our variable u. Okay, so one thing that you might look for, which is not going to show up in all integrals, it doesn't show up in these other 2, but one thing that is helpful is if you see a set of parentheses. A lot of the time, if you see a set of parentheses in your integrand, whatever's inside there is what you'll want to set u equal to. Again, this is not always going to be the case, but a lot of the time it is. So I'm going to set u equal to the x cubed minus 5. X cubed minus 5, that's in parentheses right there. Because now I could write this as u to the 55th power, but I'm not quite done yet because I also need to find du. So remember what du is, it's the derivative of this function with a dx attached to it. So the derivative of this would be 3x squared dx. Okay, now looking back up here, I want to take everything in my integrand and rewrite it all in terms of u. So if you notice, the 3x squared and the dx here all make up this du. So together, those things are going to make a du. And then what's here, the x cubed minus 5, I'll swap that out for a u and write it as u to the 55th power. I have u to the 55th power du. This is a significantly easier integral to handle than the original one was in that form. So now what I'm going to do is just take the antiderivative. Remember, you add 1 to the exponent, and then you multiply by the reciprocal of that new number. So that would be 1 over 56 times u to the 56th power plus c. But that's not really what we want our answer to look like, because the original integral was given in terms of x. So what I need to do is take the thing that I assigned to u, this x cubed minus 1, and plug that back in for the u here. That makes this 1/56 times x cubed minus 5 to the 56th power plus c. This is my antiderivative. And again, I'm not going to use the time to check this here, but it's a good exercise for you to check in your notes that this is correct. And you do that by taking the derivative of this function to see if you get back to the original antiderivative up here. Okay, let's try another one. So this function here, 9x e to the x squared plus 3 power dx. I want to take the antiderivative of that. So I said in the first example, if you're looking for what to assign u to be, it's oftentimes a good idea to look for something in parentheses. But here we have no sets of parentheses to give us that clue. So another thing that's sometimes helpful to look for, and again, this is not always the case, but if you have an exponential function in your integrand, and if the exponent in that exponential function looks like a relatively complicated function. In fact, I'm not even sure I would call it that, but something more than just an x. So notice we have an x squared plus 3 here. That is oftentimes another good choice for u. So I'm going to take that x squared plus 3. I'm going to try setting u equal to that. Okay. Now, as before, we want to find du. So du would be equal to the derivative of this, 2x plus 3. Oh, sorry, not plus 3, just 2x dx. Okay? Now compare what we have here to our integral. So I can see that by defining u to be x squared plus 3, I'll be able to write this as e to the power of just u, which is a simpler expression than what we're given. And then I have this 9x dx here. I would like for that to turn into my du so that the whole thing looks like e to the power of u du, because that's an easy integral to do. However, I don't exactly have that. I feel like I'm part of the way there. This x here I'm seeing here, but I have the wrong constant. Instead of a 9, I have a 2. So what I would like to do is get a 9 to appear there. Okay, now how can I do that? Well, if I want to turn that 2 into a 9, one thing I could do is multiply it by 9 halves. So the 2 in the denominator would cancel with that 2, and the 9 in the numerator would replace that, and it would become 9x. This is an equation, so I'm allowed to do that. I'm allowed to multiply by 9 halves as long as I do it to both sides. So I'm going to slightly manipulate this and write this as 9 halves du equals 9x dx, okay? And what that does is it gives me something that I can now use as a replacement for this 9x dx right here. So here's what the integral looks like now. It looks like 9 halves dx, or du, but the du is going to go all the way at the end. And then I have this e to the u. Remember that x squared plus 3 becomes a u. Here's the du right here. Okay, that's a significantly easier integral to deal with than what we started with. This 9/2 can come out. I won't usually write this as a separate step, but it's good to remember that you can do this. We had a property that says that constant multiples can be brought out. So the constant can be brought out like this. Remember, e to the u is its own antiderivative. So I'm going to get 9/2 e to the u plus c. But once again, e to the u is not really what we want. We want something in terms of x. So now that the integral has been taken care of, we take our function of x and put that in for the u there. This becomes 9/2 e to the x squared plus 3 plus c. Once again, highly recommend that you verify that this is correct using a derivative. Take the derivative of this, okay? We have one problem left to do. Let's zoom in a little bit there. Okay, so here we have 6x to the 4th over 2x to the 5th plus 23. Once again, we don't have a set of parentheses that are giving us a clue as to what we should use for our u. But I want to just kind of compare some stuff here. So first of all, this is a rational function. And that means it's a quotient where I have a polynomial in the numerator and a polynomial in the denominator. You'll also notice that the degree of the polynomial down here in my denominator is 5, and the degree of the numerator is 4. So the denominator has a degree that is 1 higher than the numerator. And I know that if I take the derivative of a 5th degree polynomial, because of how the power rule works, I'm going to end up with a 4th degree polynomial. So what that tells me is that if I have this 2x to the 5th plus 23 down here, if I were to set that equal to u, 2x to the 5th plus 23, I know that when I find my du, I have to take the derivative of this, and I know that the derivative will be a 4th degree polynomial. So I have this hunch that the du is going to involve that 6x to the 4th somehow. Let's find du. Du would just be equal to 10x to the 4th. Okay? So 10x to the 4th is pretty close to what we're seeing up here, but just like the last example, the constant doesn't match. And also just like the last example, I forgot my dx. Make sure you include that dx in there. Just like in my last example, I can manipulate this as an equation so that I do make a 6 appear there, okay? What I'm gonna do is multiply both sides by 6/10. 6/10 du, because the 10, when I multiply it on this side, will cancel with that 10 and be replaced by a 6. 6 x to the 4th du. Now, this is not simplified. I kind of want to see that simplified, so let's go one step further and simplify the left-hand side. It's 3/5 du equals 6x to the 4th. That should be a dx, sorry, dx. Okay? And again, what was the purpose behind that? Well, I'm trying to use trying to use my entire denominator as u, which means everything that I haven't accounted for yet, the 6x to the 4th and the dx, should be accounted for by the du term that also has to make an appearance. So now here's what we have. This integral, the entire numerator is going to become 3/5 du. And just like the previous example, I know that that 3/5 can be pulled completely out of the integral. So I'm just going to do that in this step. That leaves me with just du, which you can either put in the numerator or you could put down here. I'm going to put it down here, so there's just a 1 in the numerator now. And then we let the entire denominator be u. Okay? So now what I'm doing is I'm taking the antiderivative of 1 over u, which we know how to do. That's the natural log function. So I get 3/5 times the natural log of u. Remember, you need an absolute value around that, plus c. And then as before, we replace the u with what we defined it to be in terms of x. So 2x to the 5th plus 23 plus c. Okay? That's my answer. So really quickly, here's a quick summary of some possible substitution cases when you're trying to use substitution. And these kind of account for all three of the examples that we just did. So if you have an integral of the form some function raised to a power, as long as that power is not -1, times something, which hopefully is of the form g prime of x dx, or in the case of b and c here is just very close to that, maybe the only difference being a constant that you're multiplying by, then you want to use your reverse power rule, right? We also saw a case where we had an exponential function or where we had a rational function. In the case of the exponential function, it was helpful to let u be equal to that exponent. And in the rational function, it was helpful to let u be equal to the entire denominator. Now, again, these are not universal rules. These will not work in every single possible case, but a lot of the time they do. So think of this as a good starting point for how to set u equal to some function of x in your integrand.